Hi everyone, welcome to today's live group tutorial on GCSE Physics. Today's topic is on domestic uses and safety of electricity, and will be led once again by our amazing physics tutor Preshayla. As I've said before, if you've been here, Preshayla is a student studying physics at Loughborough University and has done lots of lessons with my tutor, and that's why she'll be leading the session today. Just a few things from me before we go into what we'll cover. Is that if you're just joining for the first time, all of these sessions are recorded and you'll be able to access links to the recordings afterwards. The way that we typically run the sessions is for the first 45 minutes, Preshayla teaches the content, and then we have the last 15 minutes at the end for questions. If you want to send questions through before then, feel free to use the chat, because Preshayla and myself will be able to see all your questions in the chat. And if there's things that you want her to clarify or you want us to maybe go a bit slower on, then just send them through and we can make sure that those are addressed for you. And so in terms of what we'll cover today, we'll be spending the first 10 minutes understanding the difference between AC and DC. Then we'll be learning about the features of a plug and the dangers surrounding them. Then Preshayla will be going through some example questions, and then at the end, as I said, we'll have time for questions. Cool, so I'm just going to hand over to Preshayla now.
Welcome back everyone. I hope you enjoyed yesterday's session, or welcome if this is the first time that you're joining us. Okay, so as Frederica said, today's session is going to be on domestic uses and safety of electricity. So it forms quite a small section of the electricity section in your GCSE, but it's really important and it gets tested a lot because it has real life applications. Okay, so the first thing that we need to know about is direct and alternating potential difference. So you might have heard it called AC and DC. So DC is the direct version and AC is the alternating version. Now, in your exam board, it's referred to as direct and alternating potential difference, but the abbreviation that we use is DC and AC. So although DC stands for direct current and AC stands for alternating current, it's important to call them direct potential difference and alternating potential difference. So that's the first thing you need to know, that there are two types of potential difference that we can have. Now DC, we get from car batteries and solar cells, any type of cell or any type of battery. And they provide a direct current that only flows in one direction. Okay, so that's the definition of DC, is a current or potential difference that only flows in one direction. An alternating potential difference comes from power stations, and it is what comes out of your socket. And the reason for this is that when electricity is being generated in power stations, we use magnets to make that electricity. So this makes an alternating current. So in the UK, the electrical supply, as I said, the stuff that comes out of your socket is AC. And it's delivered at a frequency of 50 hertz and is delivered at a voltage of 230 volts. Okay, so it's important that you know that the voltage of AC is 230 and the frequency of AC is 50 hertz. Okay, now although we use DC, AC and potential difference, yes, potential difference and current are different things, but in this case they can be used interchangeably. Okay, so moving on to the next part, what do AC and DC look like if we were to plot them on a voltage time graph? Okay, so you might not have ever seen these type of graphs before, but that's okay. We have voltage on the y-axis, so this is our y-axis here, and the same here, and that central line you can see is 0 volts. Okay, so 0 volts. So it goes up, in this region here, the top half is positive, and it goes down in this region here, which is the negative region. Okay, so AC on a voltage time graph looks like a kind of wave. Yeah, so it's always alternating between a negative voltage and a positive voltage. So it goes negative, positive, and it does that constantly. It's constantly changing direction. That's what alternating current means. Voltage constantly changes direction between positive and negative values. Okay, so if it's going negative, the current's going a certain way, and if it's going positive, it's the other way. Now, DC on a voltage time graph is just a straight line, because DC only flows in one direction, which is the positive direction at one constant voltage. And this is what we see in our circuits that we use in GCSE questions, and in school you'll see your circuit has a cell or maybe a battery like this. That is DC. Okay, so DC is in batteries and cells. So they're the two types of current that we need to know: AC, which is alternating current, and DC, which is direct current. And those link to alternating potential difference and direct potential difference. Okay. Okay, so as I mentioned before, DC is what we have in batteries and cells, in circuits that we use at school. In the power packs that you might have in small batteries, that's DC. But what comes out of our sockets, so when you plug in your charger or a hairdryer, straighteners, whatever, when you plug them into the wall, that's AC coming out of any socket. Okay, so sockets in your houses, sockets anywhere, the 3-pin socket, that's AC potential difference coming out of there. And we know this is called mains electricity. Okay, so anything that comes out of those 3-pin sockets is called mains electricity. Now, mains electricity is, as we said, an alternating current source. So the direction of the current that is coming out of your socket constantly changes between positive and negative. So it's constantly going positive, negative, positive, negative. Okay, so that's AC coming out of the sockets that we have in our houses. Now, this here you might recognize is a plug. So this is what the plug part of your charger might look like, the plug part of your straighteners. Anything that is a 3-pin plug in the UK will look like this inside. Okay, and we've got a little diagram here of all the features of this plug. Now you can see that this green and yellow stripy one is called the earth wire. The blue one is called the neutral wire. And the brown one is called the live wire. Then we have a fuse and a cable grip. So the cable grip keeps all the wires together. And then in our wire, we have outer insulation. So that's that kind of plastic coating on the wire so that they're not exposed. So the most important part of this is the earth wire, the neutral wire, and the live wire. So 3 types of wire, color-coded so that we can differentiate them, and they all have their different functions, which you're going to cover in a second. Now, these 3 wires are all made of copper. And the reason for this is because copper is a very good conductor, which makes sense because we want to conduct electricity in the most efficient way possible. And they're coated in plastic. So it's important that we don't have any wires exposed. So we coat them in plastic, which, as we know, plastic is a very good insulator, and therefore it keeps the electricity within the wire and doesn't expose it. So we can reduce our risk of electric shock. So they are the 3 wires. And then the functions of everything in the plug. So outer insulation, what's the function of the outer insulation? Well, that's just an extra bit of protection in the form of a plastic wrap around the 3 wires, keeps them all together, they're not exposed, it's all in one wire. That's basically the function of the outer insulation. The cable grip, again, kind of self-explanatory, it just holds the wires tightly together so they don't become loose and, again, exposed. Then we have the live wire. So the live wire kind of makes it all happen. And again, it's the copper wire that's coated with brown plastic. So it's that brown wire that we just saw before. And it allows our current to enter the device. Remember, it's an alternating current because it's mains electricity. So the live wire is what actually allows the plug to work and allows the current to enter the plug. Now the live wire is what is held at 230 volts. So we know that our alternating current has a value of 230 volts. Now that might sound a bit confusing because I've just said the alternating current is 230 volts, but remember we can use alternating current to mean alternating potential difference, even though the AC means alternating current. Okay, so try to get your heads around that current and potential difference can be used interchangeably in that instance. So we have alternating current at a value of 230 volts, and the live wire is always going to be at 230 volts if it's mains electricity. So in the UK only, mains electricity comes out at 230 volts. In other countries it might be different, but in the UK, and certainly for your GCSE, the live wire is held at 230 volts. Okay, then we move on to the fuse. So the fuse is a glass or ceramic canister, so it's like a little cylinder this big, containing a really thin wire that melts if the current gets too high. So if for any reason we were to have a surge in current or a sharp rising of current, the fuse can detect this and it melts the wire, which breaks the circuit. The next part is the neutral wire. Now, because it's neutral, it's held at 0 volts, and it's basically just there to complete the circuit. It doesn't have much relevance, but it is important to complete the circuit. So that's its only function, really, and that's the one in blue plastic. So remember, the wire is not blue, the plastic around it is blue. And then we have the earth wire. So the earth wire is held at 0 volts as well. Now, the earth wire is a very important feature of the plug for safety. The earth wire provides a path, a low resistance path, for the current to flow from the device to the ground, either to an electrical pathway in the ground or a water pipe in the ground if there is a fault. So if there's a fault, it protects you from electric shock by taking the current and providing a path for the current to go so that it doesn't go into your body. So it takes the current and it puts it straight into the ground rather than the current getting released into your body, which is obviously not very good. And that's a low resistance path. And the reason that it's a low resistance path is so that we can allow as much current to flow out of it as possible. So we want as much current to go to the ground as we can, which is the reason it's a low resistance path. And if you remember, that comes from V equals IR. If we have a very low resistance, we must have a very high current coming out for a certain voltage. Okay, so they are the functions of every single part of the plug. Now, the two main safety features that we have when we're talking about plugs is that the live should never touch the earth. Okay, so the live wire should never touch the earth wire, because that then makes a complete circuit from the mains to the ground, which is not a good thing. Also, if you touch the live wire, even when the switch is off, so even when on your socket panel, if your switch is off and you touch the live wire, you might still complete the circuit between the live wire and earth wire, and you'll get an electric shock. Okay, so the moral of the story is the live wire and the earth wire should never touch. The reason for this is that it makes a complete circuit from the mains to the ground, and there is then a risk of potential shock. So live wire doesn't touch earth wire. Okay, so that's all of the kind of main content that we need to go through covered. So we're going to get on to some quick kind of fire questions, which hopefully we'll be able to answer. So the first two questions here, could you all have a go? I'll give you 1 minute to think about what the answer to question 1 is and what the answer to question 2 is. Okay, so I'm getting a few different answers to question 1, so we'll come back to that in a second. But if you did write 230 volts for the second one, you're absolutely correct. Mains voltage, so what comes out of your socket, is at 230. Now for the first question, I'm getting both alternating and direct, so let's just clear that up. Now, what type of current does an electric cell produce? So if we go back to this slide, we can see that DC happens in batteries and cells. Okay, so they're the things that you use at school, like a little battery, or you might have a power pack. If you're using a battery or a cell, that's going to be direct current. Okay, the only place where we have alternating current is out of our sockets, which is called a mains electricity. That's got nothing to do with batteries and cells. That's mains electricity. That's coming from power stations. So it's coming from the power stations through the cables into your socket. That's alternating current. Okay, so that comes out of the mains electricity. But if we have car batteries, solar cells, any type of battery, any type of cell, we have direct current. So the answer to this one, because it's a cell, we produce direct current. And the answer to this one is indeed 230 volts. Okay. So the next question is, what is the frequency of mains electricity? And what colour is the live wire? So I'll give you another minute for this one. Okay, cool. I can see a lot of you getting the right answers, which is really great. So what is the frequency of mains electricity? Well, that's 50 hertz. So the two key features of mains electricity is that it's 230 volts and 50 hertz. Okay, so if we go back to this slide here, you can see that the mains electricity is frequency of 50 hertz and voltage of 230 volts. Okay, and what colour is the live wire? This is just a simple kind of memorization, a fact that you need to learn. The colour of the live wire is indeed brown. Okay, so brown for the live wire. Okay, so next two questions. Which wire is connected to the fuse? Now, I didn't tell you this exactly, but you might be able to guess which one's connected to the fuse by the definition of the fuse. So remember, the fuse is a thing that can detect the current coming through and see if there is a surge in the current, it can melt the fuse and break the circuit. So which one would that be? Which wire is connected to the fuse? Cool, I can see quite a lot of you putting live, which is great. The live wire is connected to the fuse. The live wire is kind of what provides the current, what allows the current to come through. And so the fuse needs to be connected to the live wire so that it can detect a change in current. Okay. And what is the correct description of the earth wire? So if we remember the definition of the earth wire, the function of the earth wire is to allow as a current fault to fall to ground. Okay, so it takes it away from the socket and pushes it to the ground so it doesn't go into your body. And that path needs to have a very, very low resistance. So if you put a low resistance path to ground, that's correct. The reason it needs to be low resistance is to allow as much current as it can through. So remember, low resistance is high current. So this low resistance allows lots and lots of current to flow out to ground, reducing the risk to us of electric shock. Cool. Okay, so another 2 questions here. What is the purpose of the earth wire? What is the purpose of a fuse? So you've got, these ones are quite easy because they're multiple choice, but what is the purpose of each component of the plug? I'll give you another minute for this. Okay, so the correct answers are A and C, which a lot of you put in, which is really great. So 7 is A, 8 is C. Now 7 is A because the function of the earth wire does provide a path for high currents to go to ground. So we don't want them to come to us, we want them to go to ground. The earth wire is not needed to make the appliance work, it's needed for safety. And if the neutral wire fails for some reason, the earth can't take over. That's not its function. Okay, so the earth wire provides a path for high currents to go to ground. And then the next one, what is the purpose of a fuse? Now, this is not to stop the wires falling out of the plug. That's the purpose of our bracket at the bottom. A fuse is designed to melt if a wire becomes loose in the circuit. No, not quite. So if a wire becomes loose in the circuit, a fuse is not going to do anything to help that. So the purpose of a fuse is indeed designed to melt if the current gets too high. And if the fuse melts, that breaks the circuit and it doesn't allow current to pass through, and therefore it doesn't allow current to pass into us. Okay, so got 2 more questions here. This one you might need to use an equation for, and the same with this one. So we haven't covered it yet, but I'm going to give you 2 minutes to see if you can have a go at using the equation P equals IV to help you work out what the answer might be. So P equals IV, where power is P, I is current, and V is voltage. So 2 minutes to have a go. Okay, so a few of you have had a go, which is really great. Just a hint if you haven't managed to quite do it yet. A fuse always has a rating, okay? Now the rating on the fuse is going to be a value of current. So if this is our fuse, the rating of the fuse might be 3 amps, okay? Now that means if a fuse has a rating of 3 amps, that means that if the current goes above 3 amps, the circuit will break. The fuse will melt and the circuit will break. So we need to have a fuse rating that includes the current that is going through our circuit. So if we have a power rating of 900, so power equals 900, what current will we be getting if we have a voltage of 230? Well, that's going to be I times 230. Now to find I, we need to do 900 divided by 230. So 900 divided by 230 is 3.9. So I is 3.9. Now, if I is 3.9 amps, that means we have a 3.9 amp current going through the circuit, okay? So if we have a current of 3.9, our fuse needs to be bigger than 3.9. If we have our fuse at 3 amps, well, the circuit's just going to break immediately, right? Because our current is already too high for it to manage. The fuse breaks if we have a current that is higher than 3 amps, and we do. Our current is 3.9 amps. So we need to have a fuse that is bigger than our current, but not so big that it's not going to do anything if the current gets too big. So 5 amps in this example would be perfect. 5 amps. So we want a fuse of 5 amps for this circuit. And the reason that we want a fuse of 5 amps is because it's big enough to allow our normal current to go through, but it will melt if our current gets bigger than 5. And that's going to be dangerous. We don't want a current that is bigger than 5. So we want the fuse to melt if the current is bigger than 5. Okay, so that's why we would need a 5 amp fuse for this. 13 amps would be too big. If our fuse was 13 amps and it only broke at 13 amps, it would be dangerous to us because the fuse wouldn't be breaking it wouldn't be breaking the circuit even if we were to reach 13 amps, which is much too high of a current for our microwave, okay? So it's about getting the balance right for the correct rating of the fuse. So we'll try again for this one. We've got a power rating of 750 and the plug is again connected to mains, which is always 230 volts. So first things first, we need to find out the current. Now, power equals I times V. Power here is 750 and I times 230. So we divide 750 by 230 to get 3.3. So our current here is 3.3 amps. And that's our first step done. Okay, so we know the current going through our TV is 3.3 amps, but we have a 3 amp fuse. So that's not an appropriate fuse for the TV. 3 amps is not an appropriate fuse. Our current, I, is 3.3 amps. So as soon as that TV is turned on, we know there's going to be a 3.3 amp current going through the TV. But because our fuse will melt if it gets any current above 3 amps, as soon as the TV is turned on, the fuse is going to melt and the TV is going to turn off. Okay, because the current is too high for the fuse to manage. The current is 0.3 amps bigger than it should be for the fuse. So here the fuse has the wrong rating. The fuse needed to have a higher rating for this circuit to work efficiently. So again, a 5 amp fuse would have been perfect, but the wrong fuse has been put in, a 3 amp fuse, and so it's broken. Now that means that the fuse was the wrong rating. So if you got that one, very well done. That one was quite complicated. So yeah, it's just kind of really using this equation here to help us at first. P equals IV, power equals current times voltage, to find our current and then to see if that fuse is going to be appropriate. Okay, so we've talked quite a lot about fuses, but can we describe what a fuse actually does in a circuit? Now this one's not specific to plugs, but the fuse is the same no matter what circuit it's in. So describe what happens to the fuse in a circuit. What does the fuse do in a circuit? I'll give you 1 minute to think about what the answer might be. You can write it down or you can just think about it in your head. 1 minute to think about the action of the fuse in a circuit. Cool, so a few of you are getting the correct answer, which is that the action of the fuse in the circuit provides a barrier for surges in current. Okay, so the fuse will melt if the current becomes too high, and in our case if the current is bigger than 5 amps. So as soon as we get a current that is bigger than 5 amps, the fuse will melt. It just can't handle the current, okay? And it can't handle a current that is bigger than 5 amps. So if we were to put a 6 amp current through this fuse, the wire in the fuse would melt and it would break the circuit. So if you think about a wire going through here and coming out the other end, and it also is in here. Okay, so our wire goes from some component in the circuit into the fuse and out again. If that wire becomes too hot, it melts, and it becomes too hot if it gets too much current. It will melt and cause a break in the circuit. If there's a break in the circuit, current can't flow and the component or the device stops working. Okay, so that is how a fuse works, and well done to those of you who got that. Now that would be a 3-mark question. So 1 mark for saying that the fuse will detect a current that is higher than the fuse rating. So the fuse detects a current that is higher than 5 amps. If it detects a current that is higher than 5 amps, then the fuse melts. So that's the 2nd mark, the fuse melts. And the 3rd mark is that if the fuse melts, it breaks the circuit. Okay, so this one is about a hairdryer. So now we're talking about real life applications of our features of plugs. So we have a hairdryer and we have the diagram of a hairdryer, the circuit diagram of a hairdryer. Now don't worry too much about the circuit diagram of the hairdryer. It's not too relevant to what we need to understand about it. So the first question is, what colour is the insulation around the wire connected to the live pin inside the plug? So what colour is the wire that is connected to the live pin? It's just a kind of memorization, fact recall, what colour is our live? Think carefully about this. What colour is our live? Cool, I can see quite a few of you putting brown, which is good. Live is brown. And you might want to come up with your own kind of way to remember this, because it is just a simple recall exercise. So live is brown, neutral is blue, and Earth is green and yellow stripes. Cool. Okay, so why does the hairdryer not need an earth wire? Why would the hairdryer not need an earth wire in this case? This is quite a tricky question, so don't worry if you don't get it straight away. Why would it not need an earth wire? Think about the function of an earth wire. It's really there for safety, right? It takes a current and it pushes it to ground. But why would this hairdryer not need it? And it's about something to do with how a hairdryer is made. So we've got 4 different components: switches, fans, and heaters. So which one of the 4 components means that we don't need a earth wire? Okay, so some of you are saying switches. That's a really good guess, but you still have switches in a socket, and a socket still needs an earth wire, so it's not switches, so that's not going to protect you. Those of you saying plastic case, brilliant. Plastic case, plastic is a really good insulator. It keeps that electricity in so that we are protected. Okay, so the reason that we don't need an earth wire is the plastic case. Now, I think someone said that they didn't quite understand the previous question, so I'm just going to go over it again and write out the action of the fuse in the circuit. So the action of the fuse in the circuit detects a surge in current which is higher than the fuse rating. This melts the wire in the fuse and breaks the circuit so that current can't flow. Okay, so if you need a refresher, you can go back to this page after the lesson and check the definition. So hopefully that's cleared it up a little bit. Okay, so now we are going on to the next question. So here we have an electrician replacing an old electric shower with a new one, and this is the inside of the shower here. If the electrician touches the live wire, he will receive an electric shock. Why would this happen? Now, again, this one is quite tricky, so don't worry if you don't get it straight away. Why would he receive an electric shock if he were to touch the live wire? And this is quite a, I think it's a 3-mark question, so we do need to go into quite a lot of detail. And remember, the command word here is to explain. So don't just say what will happen, say why it will happen as well. Cool, so I can see quite a few of you putting great answers in the chat. It's really good. But, if you need a refresher on the functions of the live wire, let's have a look. So the live wire is indeed held at 230 volts, and this is what allows current to come into our device. Now, if he were to touch the live wire, he would indeed carry that voltage through his body. So the potential difference of the live wire is 230 volts, and the electrician is obviously held at 0 volts, right? You don't have any voltage going through your body. So he's got holding the live wire, which is at 230 volts, and he is 0 volts. That's going to complete the circuit and allow a potential difference of 230 volts to pass through his body, and he will receive an electric shock. Okay, So if you said that it completes the circuit, well done, it does. And there will be a large potential difference between the live wire and him. Okay, so the potential of the wire is 230 volts, the potential of him is 0 volts. That's a very large potential difference, and he will therefore receive an electric shock. Okay, so the next one is more of a kind of wordy question, and again, it is a recall question. So it's about you remembering facts, unfortunately, but it's just something that needs to be done. So what is the difference between an alternating current and a direct current? So have a think back. I won't show you the page. Try and remember what it might mean and use the terms alternating and direct to help you. So what is the difference between them? So someone's just asked what type of potential difference was the previous question. So the potential difference in the previous question is indeed AC, because it's plugged into the wall, right? It's plugged into our mains electricity. That's the way that the shower works. The shower does not work on a battery or a cell. It works by plugging it into the socket. So that's how that one works. It's an electric shower. Okay, so the difference between alternating current and DC current, brilliant. Loads of you are getting the right answer, which is really good. I don't think there's any wrong answers, so that's great. So alternating current, yes, it flips and it constantly changes between positive and negative directions. Direct current is just one direction. Okay. Okay, so we've got another figure here, and this time we've got a filament light bulb which is connected to the mains electricity supply. So we know it's going to be an AC current. Here we've got a plastic coating or casing, the live wire, the neutral wire, and some plastic. It doesn't have an earth wire connected. There's no earth wire in our diagram. But why is the light fitting still safe to use? So even though it doesn't have an earth wire, what else could provide that safety to us? Great, loads of you are saying that it's got a plastic case, which is really good. So yeah, because it's got a plastic safe, we are protected and there's no need for the earth wire. Okay. So we'll do this one question and then we will have some time for questions from you guys, if you want me to go back over anything, but we'll just do this last question first. Okay, so a washing machine is connected to the mains electricity supply, so again, AC, using a cable and 3-pin plug. It's our 3-pin plug here. Now, I haven't told you the exact answer to this question, but I'm hoping that you'll be able to guess what it might be made out of and why we use that material. So the outer case, what is the material used for the outer case and why is that material used? Bro, loads of you got it within seconds, which is great. So it's kind of the same as the last answer. The outer case is plastic and we use plastic because it's a good insulator. And that means that it's not going to let the electricity flow out. Good. Really well done. So I'm going to ask anyone if they've got any questions to put them on the chat now.
Hey, Preshayla, I can't see any questions yet. While they come through from you guys, do you want to run through another question?
Cool. Yeah, sounds good.
Awesome.
Okay, so this is a again kind of a wordy question. It's about your own kind of understanding of hazards. So new research has shown that many people underestimate the hazards of using mains electricity. It's important that people do understand the hazards of using main electricity. Why is it important that we understand the hazards? So it might kind of seem like an obvious, kind of weird question, but it is important for you to understand. So why would it be? Why is it important? Yeah, great. You could get injured via an electric shock. So yeah, you can absolutely get an electric shock from mains electricity in lots of different ways. And so it's very important for us to understand the hazards of it. Okay, is there a problem if we have DC in main sockets? In main sockets, you can't have DC because it's not connected to a battery or a cell. The stuff that comes out of your socket comes from power stations. And power stations create an AC current because they use magnets. And because of this use of magnets, it produces an alternating current rather than a direct current. So the electricity that comes out of your socket would never be DC, it would always be AC because there's no cells or batteries involved. Okay, so the diagram shows a 3-pin plug connected to a 3-core cable. So the standard kind of setup that we have. So the 3 wires of the 3-core cable have different color coverings, as we know. What is the color of the neutral wire? Great, if you said blue, that's correct, well done. So I just had 2 more questions there. Is a fuse a cell? No, a fuse is not a cell, it's just another component in the circuit. So it's just like a glass cylinder with a wire inside. That's what a fuse is. It's not a cell, it doesn't create electricity, it just detects electricity in the wire. Is it because magnets have north and south magnetic poles? Well, when we create electricity, it's to do with a magnet turning. So the magnet needs to be constantly moving in order for an electric current to be created. Okay, so it is, yes, kind of because magnets have north and south poles, but it's because those north and south poles constantly change when the magnet is turning that it produces an alternating current. But don't worry about that too much, it's quite advanced and it won't come up in your GCSE, but that is why alternating current is created from magnets. Okay, cool. So next question, which 2 parts of the plug in the previous diagram protect the wiring of a circuit? So what 2 parts? Brill, so a lot of you are saying fuse and earth wire, which is absolutely correct. They are our 2 important safety features of a plug. Now, I've had a question about a battery charger. I'm assuming you mean a car battery charger. So if you are charging a battery, you're going to connect it to a socket, I'm assuming. So what you want to do is connect it to the socket. That's going to be AC, and the AC is then turned into DC, and a battery charger needs to be charged with DC. Okay, so next question. The radio can also be powered by a battery. What type of current does a battery supply? What type of current does a battery supply? DC. Brilliant. So we always have DC if we have a battery. Okay, so here, this is about the wiring of a plug and which wire goes to which point on the plug. So what one does the live go to, A, B or C? What one does the earth go to, A, B or C? Or which one does the neutral go to, A, B or C? So I give you a minute to think about what that might be. Okay, so I didn't show you the wiring per se, but the live wire does goes to C, and you can see that it's connected to the fuse, so that's how we know. The neutral wire goes to A because it's just a circuit completion feature, and then the earth wire goes to B, which is this top one here. Okay, so the answers for that would be C for live, A for neutral, and B for earth. Okay, so I've had a question about how do AC-DC converters work? Well, that is with a very complex mechanism which you don't cover until degree level, but the short kind of answer is with a rectifier. So if you do want to have a go and go away and research that yourself, it's called a rectifier, and that's how we change AC to DC. Okay, so moving on to the next question. Okay, so here we have an incorrectly wired 3-pin plug. So you can see we've got the earth wire there, we've got the neutral wire there, we've kind of got all the components, but it's incorrectly wired. What two things make it incorrectly wired, and what do we need to change about them to make sure that it is wired correctly? Cool, a lot of you have noticed that the earth wire is not connected properly and is exposed, so that's very good. And the cable grip is obviously not attached, so you can see that the screws come loose. So the answers to this would be screw the cable grip in properly and connect the earth wire properly as well, or again. Okay, so I'm going to leave that one. Okay, so here a householder rewires a toaster with a new cable and a plug. Explain why this toaster might not be safe to use. Why wouldn't this be safe to use? You've got to be quite, you've got to pay attention to detail in this one because it might not be clear as soon as you look at it. Brill, well done. So a lot of you are saying that there's no earth wire that's great. That's the what, but why? Why would that make it not safe to use? Why would not having an earth wire mean that it's not safe to use? And the answer to that would be, well, if there's no earth wire, then there's no path for the current to go to the ground. Okay, so there's no path for the current to be grounded, and therefore it could cause harm to us. Okay, so again, this is a correctly wired 3-pin plug. What colour is the insulation around X? And what name is given to the wire labelled Y? Great, well done if you said blue, that's correct. And well done if you said earth. So blue, because it's the one connected to this pin and it's on the left. And what is the name given to the wire labelled Y? Well, it's the green and yellow stripy one, so that's the earth wire. Okay, so I think we should be able to answer this question really quickly now. So what is the colour of the earth? What is the colour of the live? What is the colour of the neutral? Just as the last question to wrap things up and make sure everyone's really understood. Brill, yellow and green stripes, brown and blue. Great.
Cool. So if there are no more questions, guys, we've got kind of just a little bit over a minute and a half left. So if you didn't join right at the start, just to say we've recorded the session for you, and you should be able to get a link to that afterwards. Just one final thing from me is, if you haven't already signed up to the online school, then make sure you're signed up to that, because that's how you'll be able to get emails letting you know what sessions are happening on which days, and also providing the links to those sessions. If you sign up, you'll also be able to access the Content Hub, which is basically where we're keeping a timetable of all of the live sessions that are up and ready for this week. So make sure that you are checking the online school landing page and have signed up to that as well. So I think our hour is up. But once again, thanks to Preshayla, thanks to everyone for joining us, and we'll see you tomorrow again for another physics session at the same time. Have a good day. Bye, guys.
Bye, thank you.